Hello everybody, this is my video for notes for electricity. So let's get started. Today in class we took notes. These are those notes. I'm just doing them again in a shorter, more compact version. So if you missed anything, these are those notes. Today in class I said that there are three types of electricity. And it's very important, especially when we get into chemistry, to know that electricity is simply the movement of electrons. Way back before we knew about protons, neutrons, and electrons, people knew about electricity, but they didn't know if they were positive or negative charges that were moving. So they had to make a choice, and they chose positive. They said that what we now call electricity, they said that that was a movement of positive charges. We now know that electrons are negatively charged, so even though electricians many times still talk about electricity being the movement of positive particles, what is actually moving are electrons, which are negatively charged. So there are three types of electricity. There is static electricity, and you know that from class pretty well, because static electricity is the Van de Graaff generator. It is the balloons that I rubbed with the rabbit fur today in class. So balloons, and it is, especially if you have a younger sibling, you know static electricity as dragging your feet across the carpet in the middle of winter and zapping a little brother or sister and giving them a good zap. That's static electricity. Static literally means, in a dictionary, still. So if you get a whole bunch of negative charges built up on something, eventually that charge is going to build up to the point that it can't hold anymore and it goes somewhere else. That's called a static discharge. That's what lightning is. But even though we're going to have fun with it with the Van de Graaff, and you guys can mess around with the balloons if we have time, the main reason that we talk about electricity is because of AC, which is alternating current, and DC, which is direct current. Now, we could spend hours, days, talking about the history of alternating current and direct current. But the main thing I want you guys to know about alternating and direct, the main thing I want you to know about alternating today is the fact that that is what comes out of a wall outlet. And DC is what comes out of a battery. Now, alternating literally means that the electrons are alternating their direction. They are going back and forth. Somewhere nearby, there is a power plant that is probably burning coal, making steam. That steam is then turning a turbine, which is attached to a magnet inside a coil of wire, and that magnet turning inside of a coil of wire is causing the electrons in that wire to move back and forth. It's doing it so powerfully that it causes the electrons in all the wires for hundreds of miles around that power plant to move back and forth. You plug something into a wall, and notice there are two prongs in a wall outlet. It causes that loop that has now formed to cause those electrons to move back and forth in the wire. That's alternating current. Now, if you plug something into a battery, the electrons just simply go in a big loop. So you'll notice that when you put batteries in something, one of them is upside down. It's because you want to get a circuit, a circle, a loop going through those batteries and through whatever the piece of equipment is. So that is alternating current and direct current. Alternating current was developed. A big person to know with alternating current is Nikola Tesla. The big person who advocated for direct current was Thomas Edison. Now, these two guys were friends. They kind of started going their separate ways on what they thought was the best way to power a community, a house. Luckily, Tesla won, because if Edison would have won this argument, we'd have a power plant on every community. Every square mile would have its own power station. That doesn't happen. I don't even know where the power station that turns the lights on at my house or here at New Augusta on. But luckily Tesla won this argument, and we should be lucky, because if Edison would have won, besides having these big ugly power plants every square mile, we'd also probably be out of coal by now. Alternating current just doesn't take the energy from other things like coal or nuclear to make the same amount of electricity. We get a lot more for our coal and other things. So alternating current, direct current. And yes, as I said in class, this is how the rock band AC/DC got their name. They literally are alternating current, direct current, and notice their logo has a lightning bolt in the middle of it, all because of electricity. So back to our notes. Now I want you to get some stuff down for definitions. First definition I want you to get down is voltage. Voltage is abbreviated when we talk about it with a capital V. Your book says that voltage is related to the force that causes charges to flow. I like to think about voltage in terms of it basically being an electron pump. Think about a battery of so many volts or a wall outlet of so many volts being an electron pump that is pumping those electrons through the wire. The higher that number, the more those electrons want to go through that wire. How badly do those electrons want to move? That's why a small battery at 1.5 volts, those electrons don't want to move too fast or don't want to move too badly. 110 volt wall outlet, okay, that's more. Still not a huge number, but the Van de Graaff is 400,000 volts. Those volts, those electrons, they want to move really, really bad. They have a lot of energy and they really want to jump off of that Van de Graaff. And that's why they do, because there is so much voltage that they will jump across air to get off of that Van de Graaff. The unit for voltage is not surprising. It is a volt. And it is also abbreviated with a V. Next vocab you need to know is current. Electric current. Your book defines current as the net movement current is the net movement of charges and we need to back up. The abbreviation for current is the letter I. C is used for so many other things, like the speed of light and calories, that we don't abbreviate current with the C, we use the letter I. Current has a nice analogy between electricity and water. If we say a river, if we talk about the current of a river, we're talking about how much water moves past a certain point over a certain unit of time. We could talk about how much water goes under a bridge every minute. Well, if we talked about how much water goes under a bridge on the White River, that's going to be drastically different compared to how much water goes under a bridge over the Mississippi River. So, same analogy. If we have a high current, we got a lot of electrons going through that wire. If we have a small current, we don't have a lot. Now, though that small amount of electrons may really want to go through that wire, so it could have a low current, high voltage, or we could have a lot of electrons wanting to go through that wire, but they don't want to go real bad. They're not moving incredibly fast. That would be a high current, low voltage. The unit of current is called an ampere, that can also be shortened itself to simply an amp, but the abbreviation for an amp or an ampere is a capital A. Next vocab I need you to know is resistance. I do not like the way your book defines this, but I also am not going to make up my own, so I'm just going to go with what your book says. And your book says resistance is the tendency for a material to resist. You can see why I don't like that. Used a word to define it. The tendency for a material to resist the flow of electrons. And once again, I've forgotten to tell you the abbreviation. Resistance is abbreviated with an R. Well, that sounds like a bad thing. Resistance is why we use electricity. Because if there's resistance to electrons going through a wire, that resistance may cause heat, and we get a heater. That resistance may cause electrons to vibrate, and when electrons vibrate, they create light. That light could be a light bulb. That resistance could cause something to vibrate, a speaker, and that produces sound. So resistance is the exact reason why we like electricity. It produces heat, it produces light, it produces sound, it produces stuff we like to use. So resistance sounds like a bad thing. It's not. The unit of resistance is a thing called an ohm. The abbreviation for an ohm is the Greek letter omega. And I can't make an omega very well, so that's the best you're going to get. Ohms. The final vocab I want you to know is power. And power is the rate electrical energy is converted to other forms of energy. The abbreviation for power is a capital P. The unit for power is a watt, which is abbreviated W. I'll also remind you from the previous chapter we did that a watt is a joule per second. So how quickly is electricity being converted to those other forms we just talked about in the resistor? If so many joules of electricity are being converted per second into light, that's why we have a 100-watt light bulb. And a 100-watt light bulb is brighter than a 60-watt light bulb. A 20-watt speaker is louder than a 10-watt speaker. That's what watts mean. It's how much electricity is being converted into other forms of energy. Now I need you to quickly get down the equations that you need to know for all of this stuff. And that this is already on your worksheet, so you could stop the video if you already have these. But the first equation I want you to know is voltage equals current times resistance. The abbreviation for this equation is V equals I times R. This equation even has its own name. This equation is known as Ohm's law. And also I want you to notice that that equation can go back to our good friend that I showed you many weeks ago of taking these equations and writing them in this format, so then you could put your finger over what you want to solve for and it mathematically tells you what to do. The units we're going to use on this equation, well, voltage is given to us in volts, abbreviated with a V. Current is abbreviated, or the unit of current is an amp, which is abbreviated with an A, and resistance is an ohm, which is abbreviated with omega. So just like we just did in the previous chapter, and I taught you that work equals force times distance, force being Newton's distance meters, and then a Newton meter is a joule, I now want you to see that an amp ohm is a volt. Just like a Newton meter is a joule, an amp ohm is a volt. The second equation I want you to know is power. So let's number these. Here's 1. Here's the second equation, 2. The second equation is power equals voltage times current. This can be abbreviated P equals V times I. The units here, power is a watt, abbreviated W. Voltage is a volt, abbreviated V. And current is an amp, abbreviated A. So just like I said before in the previous one and last chapter about work, now know that a watt is simply a volt amp. A volt amp is a watt. And then the final equation to know, oh, and let's go back and do our little circle thing again. P equals V times I. That will help you on the homework. And then the third equation I want you to know is energy is power times time. E equals P times T. But now I want to slow down a little bit because this one gets a little tricky. I just showed you that the unit here, that the unit we normally do for power is a watt. Time could be many things. Usually we do time in science in seconds, but for my argument, I'm going to say that we're going to do it times an hour. And then I'm going to say that we are going to use so many watts that we usually use kilowatts. So kilowatts would be abbreviated kW, hour would be abbreviated H. These just simply go together, and the unit we get for energy is called a kilowatt hour, and is abbreviated K, capital W, H, kilowatt hour. Here's what that means. This is how the electric company charges us for electricity. If we used a 100-watt light bulb and we leave it on for 10 hours, we have used 1,000-watt hours. Using King Hector's Dad Drinks Chocolate Milk, wanting to know how many kilowatt hours are in a watt hour, we move our decimal point 3 over to the left, and we find out that that is 1.000 kilowatt hours. The electric company likes to charge something around, I want to say, 12 cents for every kilowatt hour. So that means if you leave a 100-watt light bulb on for 10 hours, you're going to have to pay 12 cents. Please don't look at that and go, that's it? You use a lot of kilowatt hours. So if Mom and Dad get mad at you for leaving a light on during the day, please don't give them a dime and say that ought to cover it. It's a little bit more than that, because you probably don't leave it on one day. You might leave it on 12 or 30 days every day, and now multiply that times 30, you're over $3. You're more like $3.60. Now, that's one light in one room. Now think about your entire house. Think about the fact that your refrigerator is always plugged in, and in the summer you're using your air conditioning. Ask Mom and Dad to see the electric bill. See how much IPL charges, and more importantly, see how much Mom and Dad pay for electricity. Final thing, I want to show you how to do number 1. This is the electricity equations worksheet number 1. I want to quickly show you how I would do this problem. 38 amps. Or sorry, start over. 38A. 3 omega. I want to know voltage. That's what I want to know. Well, here's how I would do every single one of these problems. 38A, even though I've already slipped and told you, don't just say 38A. What does that mean? It means 38 amps. 38 amps is a measurement of what? 38 amps is a measurement of current. Current is abbreviated I. Alright? 3 omega. How do I really say that? 3 ohms. What's that a measurement of? Resistance. How do we abbreviate that? Resistance is R. Voltage is V. Do we have an equation with an I, R, and a V in it? Yes, we do. It is Ohm's law. V equals I times R. Mathematically, cover up what we want to learn. And what do we do mathematically? I times R. So 38 amps times 3 ohms. The numbers give us 114, but you know me, that's not going to get you credit. You got to tell me 114 what? And an amp ohm, as you saw from the previous slide, an amp ohm is now known as a volt. But you knew that because we were looking for voltage in the first place. I hope this helps. I hope this was a lot faster than class. And I will see everybody in class.